Hello guys, good morning. Good morning to all of you. Is everything all right? Okay, so I think everything is all right. We can start now. Okay, so I think everything. So today we'll be discussing the second part of the hydrogen atom problem. Let us start with a problem. This came in June 2014. Given that PR is equals to minus I h cut del del R plus 1 by R, the uncertainty del PR in the ground state psi 0 R in the hydrogen atom is, which of the option is correct? Can you solve this problem? Good morning, Murli. Let us try to solve this problem. Look, whenever this kind of problem will be given to you and you will be given an operator, you need to operate it on some wave function, let's say psi, some function psi. Otherwise, the true behavior of the operator will not be known. So for PR, there is no issue. PR, it is given to you minus I h cut del del R plus 1 by R. What you have to find out? You have to find out del PR. So this is the uncertainty in momentum. So you know the value. It is PR square average minus PR average square. This is the formula. So you have to calculate PR square, expectation value of PR square in the state of psi 0 R, and also the expectation value of PR in the state of psi 0 R. Then you have to calculate this quantity. Okay. Good morning. Where is Harry today? What about PR square? Look, this value is, we can say, minus h cut square del square by del R square plus 2 by R del del R. Good morning, Harry. Okay, so could you understand this one? From PR to PR square, how you get this one? Look, if you just multiply this thing 2 times, you may not get this result. For this, what we have to do, I am just showing you a proof kind of thing. Okay, this is not part of the solution, maybe. I am just trying to show you how you deal with this kind of stuffs. So whenever this kind of thing is given to you, you have to apply it on some wave function, let's say psi. So you see, PR square means minus I h cut whole square, and this will appear 2 times. Del del R plus 1 by R, again del del R plus 1 by R. This is what square means. So you have to apply it on wave function psi. Now this becomes minus h cut square. Let's keep the first term as it is, del del R plus 1 by R. this will become del psi by del r plus psi by r. Okay. Now, if you just expand this, so minus h cut square. Now see del r of del psi del r. So this is del square psi by del r square plus next del r of psi by r. Okay. So you can write it as 1 by r del psi by del r minus what you can write psi by r square, because derivative of 1 by r minus 1 by r square. Now next this term plus 1 by r del psi by del r plus 1 by r square times psi. Now as you can see, this term and this term is getting cancelled and you are left with minus h cut square. If I write it in this way, del square by del r square, taking this, extracting the psi part, 1 by r del r, 1 by r del r. So 2 by r del r into psi. Now here also psi, here also psi. Therefore, we can purely write pr square, this operator is equivalent to minus h cut square del square by del r square plus 2 by r del r. So many steps are involved. Okay. So using this, we can write this one. Now you have to find out the value of delta PR in the ground state. So let us try to evaluate that. So given ground state wave function, what is the ground state wave function? Psi 0 is equals to 1 upon square root of pi a naught cube e to the power minus r upon a naught. As I told you, you have to remember this ground state wave function. So we already know that expectation value of momentum, which is defined in this way. Look, this psi 0 is normalized. So that is why we do not need to divide it by psi 0 because psi 0 is already 1. This will be equals to 0. We know this result. But what about the expectation value of PR square? Let us try to evaluate that. PR square, what is the expectation value of it? Obviously this will be psi 0 PR square psi 0. So if you write it, it can be written as bra psi 0 is this 1 upon square root of pi a naught cube. It is a real function, so there is no issue. Bra and ket will be same almost. PR square. Okay. PR square psi 0 means you have to operate this to this. So you see minus h cut square, PR square is del square by del r square plus 2 by r del r, then ket psi 0 we have to write. Ket psi 0 is again 1 by square root of pi a naught cube e to the power minus r by a naught, and you know dr. Look, if it were in one dimension, then only dx would have been added here. If it is in 2 dimension, then dx dy. If it is in 3 dimension, you have to multiply volume element dx dy dz. Now you see it is in 3 dimension, but it is in spherical polar coordinate. So here instead of writing dr, we have to write 4 pi r square dr, because in spherical polar coordinate with r dependency only, the volume element is 4 pi r square dr. Actually this is coming from r square dr sin theta d theta d phi. Okay, sin theta d theta d phi, that integration gives you this 4 pi and what remains? R square dr. So 4 pi R square dr. Is it clear till now? Where is Karthik today? Okay, now as you can see, 0 to infinity, 1 by square root of pi a naught cube is appearing twice. So they become 1 by pi a naught cube, right? This minus h cut square we are keeping as it is. Then this e to the power minus r by a naught we are keeping as it is. Next, we have to operate this whole thing to e to the power minus r by a naught. So 2 times derivative of e to the power minus r by a naught. So 1 times it will give you minus 1 by a naught. Next another minus 1 by a naught. So 1 by a naught square and e to the power minus r by a naught. Now we have to apply this 2 by r del r to this. So this will give you plus 2 by r del r of e to the power minus r by a naught. So minus 1 by a naught e to the power minus r by a naught. Okay, and this 4 pi r square is remaining as it is. Now let's take this minus here, h cut square and 4 pi. So I am writing 4 pi h cut square divided by pi a naught cube. So we have taken out the constant parts. What remains? 0 to infinity. 2 integration will remain, right? 1 integration will be, let's say, 1 upon a naught square, okay, 0 to infinity, e to the power minus r by a naught, e to the power minus r by a naught, so e to the power minus 2r by a naught and this r square dr. Okay, this will be the first integration, minus 2 by a naught is constant, 0 to infinity e to the power minus 2r by a naught, and as you can see it is 1 by r. 1 by r into r square, so that is r dr. Four pi, shouldn't we consider that 4 pi r square dr term as integral u dv method? No, that is separate, na? Look, this is actually zero to infinity, or if I write it in this way, psi 0 star pr square psi 0 into sin theta d theta d phi r square dr. Okay, so a pr square is operating only on this part, okay, and then we gathered r related terms, and sin theta d theta d phi, this part of the integration gives you 4 pi. So pr square is not applied on the volume element, okay, no? It is only applying on the kth part, this part. this. Now the confusion is clear. Let's move on. That volume, that thing is a differentiable, okay? It contains the variable. The operator doesn't work on that. It works on this kate, not on this like volume element. Now it has come into a form of standard integration. We can use the standard integration using the integration. So we know this general integration 0 to infinity e to the power minus ar r to the power n dr. This is n factorial by a to the power n plus 1. Sometimes we are habituated of writing alpha e to the minus alpha r to the power n dr, n factorial divided by alpha to the power n plus 1. So if you use this integral, then we can write PR square expectation value is equals to pi get cancelled, so minus 4h cut square by a naught cube into 1 by a naught square, and this integration alpha is equals to 2 by a naught for the first case. So it is and r square is there, so 2 factorial divided by 2 by a naught, square was there, so n plus 1, so cube minus 2 by a naught, here it is n equals to 1 factorial, 2 by a naught, 1 plus 1 2. So we are getting closer to our final answer, minus 4h cut square by a naught cube. This one you see a naught cube and a naught square. So what you are left with a naught by 2 by 8 4 minus this one is a naught, right? A naught 2 by, so a naught by 2. This is how much? Minus a naught by 4. So a naught square, 4 get cancelled, so h cut square by a naught square. So when this is done, the momentum is spread, therefore the uncertainty in momentum delta PR square root of PR square minus PR whole square. So this is nothing but h cut by a naught, and that precisely matching with option A. Is it understood? Just tell me one thing. We know that hydrogen atom has this energy values, En is equals to minus 13.6 by n square electron volt. So for n is equals to 1, we get E1, let's say minus 13.6 electron volt. So can you tell me, does it mean that the energy levels of hydrogen atom are non-degenerate? Is there any degeneracy? Expectation of PR is equals to 0, because for real function, expectation value of momentum is always 0. This is true always. We have also already proved it. You can also calculate it in this way, you will get it 0. So you can also write it as a note. Without calculation, you can say expectation value of the momentum operator is 0. Here it is not momentum, but the minus 1h ka del del r, this is related to momentum, and this 1 by r, so expectation value will be 0. Okay, we can just write it as a note. Good question you asked. Expectation value of momentum for a real wave function is 0. Okay, so what I was talking about, energy level of hydrogen atom. So is it non-degenerate? Understood my question? For n equals to 1 we are getting E1, for n equals to 2 we are getting E2, and so on. Does that mean the energy, the hydrogen doesn't have any degeneracy? Can anyone tell me? Murli, Harry, Kartik, Fatima. What do you think? Look, it appears to be that it is non-degenerate, but it actually degenerate. Let me show you how. What is the degeneracy of hydrogen atom? Look, degeneracy of hydrogen atom. Look, we have the principal quantum number n. Now, corresponding to a value of n, L value will run from 0 to n minus 1. So, one value of n will give you, you can see n number of values of L. And for a particular value of L, ml will run from minus L to plus L. So, you can see it has 2L plus 1 number of values. And ms, let's say for hydrogen atom we have electrons, so ms can take values plus minus half. Hydrogen atom has single cell. No, it is, you can consider it in this way. Very good question. I also got this kind of queries initial times. Okay. So, let us say hydrogen atom has this positive nucleus. Nucleus is remaining same. Now, the electron is revolving in the Bohr's orbit. Okay, this is in the ground state. Now, when the atom is getting energy, the electron will go to the next state. Let's say this is n equals to 1, so it will go to n equals to 2. So, it will, if you provide energy, this electron will absorb that energy and will be promoted to this level, and this will be empty. Okay, so it can go up to indefinite level now. Let's say if it is coming from n equals to 4 to here n equals to 3, it will emit radiation, and that radiation is the characteristic radiation you see. Okay. Yes, if the wave function is given to be real, the expectation value of momentum will always be 0. Now you see, what will be the degeneracy? Therefore, the degeneracy. Let's say without considering spin, without considering spin is equals to, you see, how many values of ml is there? 12 plus 1. 12 plus 1. Okay. Now, how many values of L is there? L runs from 0 to where? N minus 1. So, if you put the values of L, so you get 1, right, plus L equals to 1 you put, then you get 3, L equals to 2 you put 5, and so on up to this n minus 1, 2 into n minus 1 plus 1. You will get this term. So, this is simply algebraic series, and this will give you n square. This is simply arithmetic series, or not algebraic, arithmetic. Now, for spin value, you see, two values are there. So, if spin is included, then the degeneracy of the atom is 2 times L is equals to 0 to n minus 1, 12 plus 1, this will is 2n square. You can imagine in one go, it may appear to be, the energy level of hydrogen atom may appear to be non-degenerate. Okay, En minus 13.6 by n square electron volt. If you choose n is equals to 1, En will be, E1 will be minus 13.6 EV. N is equals to 2, if you take, you get E2 minus 13.6 by 2 square electron volt in this way. So, it in one go it may appear to be non-degenerate, but if you closely look at the corresponding wave function, what is the corresponding wave function? Psi n L m. This is how the wave function is given. So, although the energy level is decided by the principal quantum number, it has also dependency on L and m. So, that is why corresponding to a single energy, there may be different number of eigenstates. Okay. So, for this, if it is nth state, the degeneracy will be n square if spin is excluded. So, a state designated by the principal quantum number n will have n square number of eigenstates. So, means n square number of states will be having the same energy as this energy. How n square is getting? You apply the arithmetic progression. The sum is given by, in arithmetic progression, this in arithmetic progression, sum of n number of terms is n by 2 times 2a plus n minus 1 into t. Or you can also write it, if there are n number of terms, n by 2 into a plus l, where l is the last term, a is the first term. So using this formula we get this n square term. Okay. Just put this formula. I think it is very straightforward. N by 2, because total number of term is n. A is 1 plus L is this term, 2n minus 2 plus 1, so 2n minus 1. So 1 get cancelled, so n square. Clear? Is 2 representing spin up and spin down? Yes, two values. Because we are considering hydrogen atom, so it is talking about the electron. Electron has a spin half, S is equals to half. Corresponding to half, we will get ms either up or down. Let's move on. Radial probability density. This is very important. Radial probability density. Probability density we have already known previously. Mod psi square dr, that is probability density. Now when I am talking about radial probability density, it is little bit different. Similar but little bit different. Radial probability density. We need to notice something here. It is denoted by P of R dr. Look, normal probability density is given by, let's say, the wave function is square. Here it is radial, so R square radial part RNL whole square dr. This extra R square is coming because of the dependence of 4 pi R square. So that R square is coming. So whenever radial probability density you are being asked, you have to multiply R square and the radial part of the wave function square. Okay. Now radial probability density, if you want to calculate for the ground state of hydrogen atom, how it will be. Let's take an example. So we know the ground state of hydrogen atom. Ground state of hydrogen atom, psi 1 0 0, this is the ground state. The normalized wave function is 1 by square root of pi a naught q e to the power minus r by a naught. So this we derived from the product of the radial part of the wave function. N is equals to 1 here. So you write RNL into y LM, you write na, L is 0, M is 0. So here what value of R10 we found on the last day? If you remember, it was a prime by a naught e to the power minus r by a naught. It was there. Then we found the value of a prime and ultimately we got it 2 by a naught to the power 3 by 2 to the power minus r by a naught. You can check the previous day's copy to get this value. So if r a naught or R10 is this, then what is the radial probability density? Therefore the radial probability density, this will be P of R dr is equals to R square R10 square dr. R square R10 mod square, so 4 by a naught cube e to the power minus 2r by a naught dr. Okay. A naught, you know, it is the Bohr radius. Now if you want to calculate what is the most probable distance of the electron in the first orbit, means in the Bohr orbit. Look, you can imagine it in this way. This is the proton. The electron, although classically we represent it to circle around in a circular path, but quantum mechanically this is not the case. It is like a wave function, okay, like this. So it maintain a constant distance, you can say average distance, and there is another thing called most probable distance. So what is the most probable distance? Most probable distance. So where this probability will be maximized, so dpr by dr is equals to 0. This is for the most probable distance. Most probable distance, dpr by dr equals to 0 at whatever value of r you get, that will be the most probable distance. So if you take the derivative of this function, you will end up getting r naught is equals to a naught. Okay, let's do the calculation. I think then it will be easier for you to understand. Look, this constant part 4 by a naught cube, that can be absorbed, or you can also write it 4 by a naught cube. Dr, let's avoid dr, r square e to the power minus 2r by a naught. So derivative with respect to r, so 2r at r equals to r naught, e to the power minus 2 r naught by a naught. Next derivative of this thing plus r square r naught square e to the power minus 2 r naught by a naught into derivative of minus 2 r by a naught, so minus 2 by a naught. Okay, this is equals to 0. Now absorb all the constant part and exponential part. If you take exponential part common, 4 by a naught cube is absorbed with 0. E to the power minus 2 r naught by a naught, that cannot be 0, so it is also absorbed. You see this 2 is also absorbed. So what you are left with? You are left with r naught is equals to a naught. This is the Bohr radius. So the most probable distance in the ground state is the Bohr radius. So if you plot this radial probability density P of r, radial probability density P of r versus r, so you can see this is a function like this. So it will be a function like this. So the most probable distance is this one, and that will be obtained at r is equals to r naught, that is at a naught. Understood? Murli, what are you asking? Why are we excluding spin of electron? We are not excluding actually. Sometimes in the question paper, to make it convenient, they ask that you can ignore spin. If it is explicitly asking to ignore spin, then you will write n square. If it is asking you to include spin, you can write 2n square. That is what it is. Does it make the calculation very complicated or any other reason behind? No, why is the complication? It's just multiplying of 2 because of the 2 possibilities. Okay, na? This degeneracy is coming because of these many possibilities in each case. Any more question, guys? or everything is all clear now? Tell me, then we will move forward. Karthik, Mullihari, Fatima, tell me. Sir, it is the most probable distance of electron. Yes, when you are taking derivative of the probability, okay, probability with distance means what? It will give most probable distance. So most probable distance means at what distance you are expecting the particle or the electron to be found most. Getting it? You can just decode this most probable distance. So that is why we take the Bohr radius A naught. So it will be mostly remaining at A naught. Psi NLM we are using, but don't psi NLM. Yes, look, this for radial probability density we only need the radial part. Okay na? Psi NLM. This is consisting of two parts, na, RNL of R and YLM of theta phi. Psi NLM of theta phi. This is RNL of R, YLM of theta phi. So for a radial probability density, we need to only consider the radial part along with R square. R square must be multiplied. And simple probability density, we have to go with the wave function psi. Look, now different electron wave function of atomic hydrogen, RNL of R. Remember this one, RNL of R. So when I am plotting 3s, what does it mean if you decode 3s? So what does this 3 means? The principal quantum number, n equals to 3 and s is equals to, s corresponds to L equals to 0. Okay, na? Look, if I talk about n is equals to 3, how many values of L you will get? 0 to n minus 1. So 0, 1, 2 you will get. So when you combine 3, 0, you get the state 3s. 3, 1, L equals to 1 corresponding to P, you get 3P. 3, L equals to 2 is D. So 3s, 3P, 3D. And the plot looks like this. This is the plot of 3s. As you can see, it has a node here. Node means where the wave function is vanishing. Then it is going like this. This is 3P, then it is 3D. 2s, 2P. 2s, 2P. Why 2s, 2P? Because if you take n equals to 2, the allowed values of L are maybe 0 and 1, because L runs from 0 to n minus 1. So when you take 0, 2, 0 means 2s, 2, 1, 2P. So that is what you get 2 wave function. 2s, 2P. Most probably distance means finding out electron. Most probable distance means, okay, let me just make it clear to you. What is most probable distance? Look at this example. Let's say this is this pointer is the electron. The electron is moving like this around the wave function. Actually, this is not the particle, actually, like this. So most probably, or the most probable distance are A naught, right? So if you consider a distance like this, most of the time you are seeing the electron in a circular path of radius a naught. So what is this distance? Most of the time it is remaining at a naught. This distance is a naught. Getting the meaning? It is you can see it is remaining at other distance as well. It is remaining at other distance as well, but the probability is less. If I consider it like this, I am just showing you one of the ways. So just a rough example just to make you understand. This is a naught, let's say, in this way. Where the probability of being is maximum, that is the distance. Okay, so this one is you understand 1s, if you take n equals to 1, then only L is equals to 0 is there, so that is how you get 1s. Now to understand this behavior of these wave functions RNL of R, we need to follow certain properties. The radial wave function RNL of R of hydrogen atom, number one, you see it will vary as r to the power L for small r. Number two, it will decrease exponentially at large r. Number three, it has n minus L minus 1 radial nodes. Radial nodes means the radial part of the wave function vanishes this many times. Radial nodes not including r is equals to 0, because at r is equals to 0 everywhere almost it is 0. So that node is not considerable. Other than that, let's say if you consider for 3p, for example, for 3p state, what is the n value? N value is 3. So how many nodes, L value is equals to 1. How many nodes you are expecting? N minus L minus 1, 3 minus 1 minus 1. So 3 minus 1, 2, 2 minus 1 is 1. So in 3p state there should be one node, and where is that one node? This is this node. So this is the one node. Okay. Now if we calculate for 3s, let's say for 3s n is equals to 3, L is equals to 0. So n minus L minus 1, 3 minus 0 minus 1, so 2. You can see one node is here, another node is here, 2 nodes. Understood? So in this way you can identify this radial part of the wave functions. Let me know if there is any confusion. Acha, so you all got little bit of confusion regarding the most probable distance. So let me just give you the definition here of most probable distance. Most probable distance is the distance where the electron is most likely to be found out. Understood now? For the hydrogen atom in the ground state, it is A0, the Bohr radius. So if the hydrogen atom is in the ground state, most likely it is found to be at a distance of A0. (3D) is cutting on R line or behave like asymptotically. 3D. No, it will exponentially, it will go on like this. Exponential decay, you know the meaning. It will not cut. It will keep on going. It is supposed to cut at infinity. This is also supposed to cut at infinity. Some more wave function, you can see some radial wave, part of the wave function, the plot looking like this. Look, here the difference is shown. This is the radial part, 1s, 2s, 3s, and r square times capital R square, means this is plotting the radial probability density. Okay, this is a wave function, radial wave function, and this is the plot of radial probability density. So for 2s it is like this, for 3s it is like this, for 2p it is like this, the radial probability density is this, for 3d it is, for 3d the radial probability looks like this. So you can write it, it is radial wave function, and this is radial probability density. Plots of radial wave function and radial probability density. So I have attached another picture just to make it more clear to you. So these pictures are just for a reference. Once you understand, you will be able to understand it. 1s, 2s, 2p, 3s, 3p, 3d. This is the plot of the radial probability density. Look, here you notice one thing. This is 1s, so ground state. A0, 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 A0. A0, 2A0, 3A0, 4A0, 5A0. So this is A0. So the most probable distance for the ground state is A0. The most probable for other state is may not be A0. Okay, you can see for this 2s or 2p it is different. For 2p it will come around some point like this. So it will be more than A0, something like this. Yeah, it is exponentially decaying. The way you plot exponential minus x, how do you plot? You plot it like this, na? Exponential. So this is supposed to meet at infinity. So we cannot show the graph like up to infinity. So that is, we just show a portion of it and we show it like this. So it is not touching. You should not show it to be touching this. It will be constantly decreasing, but it will not touch. Let's see what kind of problem can be set from this. Look at this problem. Tell me the answer. The ground state wave function for the hydrogen atom is given by this plot of radial probability density of the hydrogen atom in the ground state. Each. Which option is most appropriate according to you? N square A is equals to most probable, is it? Option D. Yeah, good observation. Murli. N square A is the most probable distance. Can say it. N square A0. Okay, you will check this. Okay, you will verify this. So prima facie it is appearing, and some result is showing this, but needs to be verified. But it is seems to be true. Okay, you are getting 2P. Oh, option D. Yes, option D. Because when you know that it has a maximum at A0, so this value is 1. Okay, now. So option D is the correct option. What is the explanation? It's straightforward. Okay, which of the following represent 3p radial wave function of the hydrogen atom? Give it a try. In the last case 4A0 for 2p case. Yes. Now this is the test. Without looking at the graphs, previous graphs, you just tell me which of these following represents the 3p radial wave function. 3p radial wave function of the hydrogen atom. 3p. So what will be your testing method to get the correct one? 3p. 3p. N is equals to 3, p means L is equals to 1. So I think by looking at the nodes n minus L minus 1, 3 minus 1 minus 1, 3p, there will be only one node. So here it is 2 nodes, so this option is discarded. Now here we have one node, here we have one node, and there is no node here, so this is also not correct. So out of these two we have to select. Okay, so how do we select? We have to go to the properties. It varies as r to the power L for small r. Okay, so when r is small, something to the power 1, so it will be near about 0, and it decreases exponentially at large r. Okay, now, but this is not the case. It is not small at this initial point, so this will be the option B. Why are we taking L is equals to 1? Because L is equals to 0, 1, 2, 3. 0 corresponds to S, 1 corresponds to P, 2 corresponds to D, 3 corresponds to F. And here 3p, the first number shows the principal quantum number. Second give you the orbital angular quantum number L equals to. Understood, Fatima? Let's move on to the next question. Okay, so you can remember this. Look, this was the graph for what was this was 3s, right? So you see, for 3s, just try to notice here, it is not 0 at r equals to 0. It should be varying as r to the power L. So for, if you consider 3s, let's say, so n is equals to 3, L is equals to 0. Now r to the power L, it varies at r to the power L. So r to the power 0. So that is why it is not 0, it is 1. Okay, or it is proportional to 1, you can say. Maybe more than 1, but it is not 0. Okay, now this one, an electron is in the ground state of a hydrogen atom. The probability that it is within the Bohr radius is approximately equal to Look, an electron is in the ground state of a hydrogen atom. The probability that it is within the Bohr radius is approximately. Okay, before solving this problem, let us try to understand what it actually asks. You know, it is in the ground state, right? Ground state. Ground state means psi 100. Okay, and we have already plotted the ground state. P of R dr. This is the radial probability density versus R. So we have seen it is like this. So what is the probability that it will remain between within the Bohr radius? Within the Bohr radius means up to a naught, isn't it? So you have to find out area of this thing. Physically, if you think, it is talking about this area. What this is the probability, right? Try to follow this. What will you do? So let us do the solution. The probability that the electron will reside will be within the Bohr radius is psi star psi 0 star psi 0 into the volume element 4 pi r square dr within Bohr radius means 0 to a naught, where this psi 0 has the value normalized 1 by square root of pi a naught cube e to the power minus r by a naught. So we need to find out this value. So 4 pi psi naught square psi naught, this is real wave function. So pi a naught cube is appearing twice, so square root is vanishing, 0 to a naught r square e to the power minus 2r by a naught is appearing twice. So this is what you need to find out. Now you can do it by the method of integration by parts. Okay, na? Integration by part you can use to calculate this one. U v, so u integration v dv r square e to the power minus 2r by a naught divided by minus 2 by a naught, so minus a naught by 2, limit 0 to a naught, minus integration of du dx, integration of this one is okay, integration derivative of the first function, so 2r, the integration of the second function e to the power minus 2r by a naught, okay, minus a naught by 2 will come, and dr is there. Is it clear till now? Tell me, then we will go to the next step. Is this last line clear to everyone? Now once again, look, we wrote it for r square e to the power minus 2r by naught. Now again we have got an integration involving r e to the power minus 2r by naught. So we have to do another step. Option B, you are getting 90%. So you can even say that it is not possible. Is it looking like 90%? The picture may not be perfect. Actually, the perfect picture, where is the perfect picture? Perfect picture is this. Okay, na? So actually, this much. Does it looking like 90% of this total area? It is looking like less than 50%. We are expecting less than 50%. Let's calculate. Just tell me whether up to this you have understood the calculation. This is equals to 4 by a naught cube. How much will be this? A naught square and a naught square, a naught cube. So a naught square e to the power minus 2r by a naught minus a naught by 2, and if you put r equals to 0, this is 0, minus, look, 2r e to the power minus 2r by a naught, then minus a naught by 2 minus a naught by 2 will come. So this is between 0 to a naught, minus minus plus, then derivative of r is 1. So you get 2 to the power minus 2r by a naught minus a naught by 2 minus a naught by 2, again integration minus a naught by 2 will come, 0 to a naught. Tell me, is there any confusion in understanding this? 0.32, yes, 0.32 will come. So this is 4 by a naught cube. How much is this value? A naught square e to the power minus 2 a naught, it will be 2 a naught, not 2r. We have to put the value of r now, minus 2 a naught by a naught. So e to the power minus 2 minus a naught by 2 minus, if you put the values, 2 a naught square by 4 to the power minus 2 a naught by a naught, so that is minus 2 minus a naught cube by 8 and this 2, so 4, it is minus 2 again. Another, there is no r term, so if you have to put 0, so e to the power 0 is 1 plus 2 to the power minus 0 a naught cube by 8. So if you calculate this one, 4 by a naught cube minus a naught cube by 2 times 1 by e square minus a naught cube by 2 1 by e square minus a naught cube by 4 1 by e square, and here plus a naught cube by 4. So 4, a naught cube is cancelled, a naught cube, a naught cube, a naught cube, every a naught cube is cancelled. What we are left with? Minus 1 by 2 square minus 1 by 2 square minus 1 by e square. So minus 5 by 4 e square plus 1 by 4. This is equals to 1 minus 5 by e square. 1 minus 5 by e square. E square is 0.5 Okay, 1 by E square is 0.137. So 1 minus 5 by E square, if you calculate, five by E square, I'm getting 0.676 almost. So this is approximately 0.323, and that is, you can approximate to be 32%. Option D. Why your hydrogen atom first lecture is not showing? No, that was live only, Prajwal. Attend the class live. Okay, is it clear? Now, just simple logic we can use. Simple logic is there that if the ground state, probability density for the ground state P of R dr versus R, so it is looking like this, we can say like this. So if I am saying that this is 32%, so what does it represent? It represents the probability in the ground state to be within the Bohr radius. Within the Bohr radius, it is 32%. So what will be the probability for the particle to be outside the Bohr radius? Outside the Bohr radius means it is referring to this region, right? It is referring to this region. This is the outside the Bohr radius. What will be this percentage? Obviously, it will be around 68%, isn't it? Now look at the pattern of CSR. It asked you at June 2014. Now in December 2018, what did they ask you? If the position of the electron in the ground state of a hydrogen atom is measured, the probability that it will be found at a distance r greater equals to or not, means beyond Bohr radius, is nearest to. Even without calculation, you can check option B. Because you know that the probability for the electron to be within Bohr radius and beyond Bohr radius, total will be 1. So probability that it will be beyond Bohr radius, 1 minus probability that it will stay inside the Bohr radius, 1 minus 0.323, so approximately 0.66, you can say, approximately, actually 0.68 or something. So even without any calculation, we can choose option B. Possible, please make available that lecture. Okay, Prajwal, I will make it available for you. But try to attend the class live if you want to attend. Otherwise, you can join the course. Okay, there you will get everything. Okay, do this one. The normalized ground state wave function of a hydrogen atom is given by this. The expectation value of 1 by r square is. This is the last question, then we'll wrap up the session and hydrogen atom will be over. Can you do this? Most welcome, Prajwal. Can you do this one? Ground state wave function is given to you. Instead of A naught, they have used A. You have to find out the expectation value of 1 by r square. So it is very simple. This came in gate. Okay. Let's try to do this. Expectation value of 1 by r square. So the simple straightforward formula for the ground state is psi 1 by r square psi. Psi is the ground state given by you see 1 by 4 pi into 2, 1 by 4 pi 2 by a to the power 3 by 2 e to the power minus r by a. So it is 1 by square root of pi a cube e to the power minus r by a. So actually a naught is replaced by a. So don't get confused. So this is psi star 1 by r square psi d cube r, right? In 3 dimension we write the volume element. If it has only explicit r dependence, we can write d3r. You know, d3r is the equivalent to 4 pi r square dr. Okay, the way we write dx for 1 dimension, here for 3 dimension we will write d cube r. D cube r means 4 pi r square dr. So this is written as 4 pi integration r square is getting cancelled, so psi star psi. So what you are left with, 4 pi into 1 by pi a cube integration r square is cancelled, so you are left with e to the power minus 2r by a and dr is dr. This is 4 by a cube, 4 by a cube. Another thing, the limit of r is from 0 to a, 0 to a or infinity. The limit of r is 0 to infinity. So e to the power minus 2r by a dr, what is the value? E to the power minus 2r by a divided by minus 2 by a. Limit goes from 0 to infinity. 4 by a cube, if you put r is equals to infinity, to the power infinity is 1, so 1 by e to the power minus infinity, that is 0, and if you put 0 and minus plus, so 2 by a means a by 2. 2 by a square actually. Is there any option? Yes, option D. Okay guys, so this is all for this session. I hope you find this session useful. From the next day onwards we may start perturbation theory. Okay, perturbation theory will take a lot, maybe 4-5 lectures maybe. So the next week will mainly deal with perturbation theory. Okay, so this is all for this session. Bye bye, take care, have a great day. Anything you want to say, guys? I'm ending the session. Bye bye.